Hey, welcome everybody. Thanks for joining us today on DEFCON 1 Science. This is going to be our kind of our new thing that we do on Sundays with Landon Curt Noll, hopefully when he's available. And today we actually got not just Landon Curt Noll, we got Dr. Rachel Traylor with us. You guys might remember her from joining us on the Non Sequitur show. But before we kind of jump into this and kind of explain to you guys what DEFCON 1 Science is going to be about, I do appreciate the live chat telling me that they can actually hear, because you know how annoying it is when you start one of these things and nobody can hear anything. Not that that's ever happened before, but well, it didn't happen this time. This is good. So I spent a lot of time trying to arrange all the audio and the video. So I do appreciate that you letting me know that you can actually hear us. If anything changes throughout the discussion here, please let us know and I'll try to change it on the fly. But anyways, what we're going to be talking about today is a little bit about what is truth, what is proof, what is the philosophical things, what are the mathematical things. But let me get to my guest here. First, we got the wonderful Landon Curt Noll. How are you, Landon?
I'm doing well, and how are folks doing today?
I hope they're doing well. I'm doing wonderful. Rachel, how are you?
I'm doing okay.
So everybody's doing great. That's great. And they can actually still hear us, which is actually really good. Just to let you know, we have started a new channel. It is the DEFCON 1 Science channel. However, I am streaming to this particular channel, and then later on I'll upload that as more of a repository of these types of things as we kind of go along throughout the weeks. But obviously that channel only has like 2 subscribers right now, so there's really no reason to stream to it live, correct? So, Landon, why don't you go ahead and tell people about yourself a little bit, people who don't know who you are. By the way, how do you not know who Landon is by now? But just in case you don't know who Landon is, let them know.
Well, I am an astronomer and planetary scientist. I also enjoy number theory as a particular branch of mathematics. And I'm also, I study, primarily study planets, but I also study mathematics. As one of the things I found was that within physics and astrophysics, one of the cores of what you do is involving mathematics. As a kid, I was always fascinated with the universe around me, and I get to live in my favorite universe. So that sense, my first complete sentence I spoke as a kid was, "How far is the sun?" And I've been asking questions ever since. Numbers always also fascinated me, and the relationship numbers got me interested in elementary number theory, and from there, it's life.
Well, let me ask you, did you have any choice other than to live in this particular universe?
No, but I mean, given the set that I can choose from, the one that I'm in is my favorite.
Was it a free will choice? Because it's the only choice you have. Yeah, I don't think you have much choice in the matter. But that's a philosophical type thing.
Yeah, and I'm sure we can bring in the axiom of choice so far. But no, but
now we're really going. We haven't even started the show yet. We're already talking about axiom of choice. Wonderful. People are going to be tuning out left and right now.
I as a positive person, and I really enjoy studying the universe, particularly planets, because planets are kind of like one of the culminations of what the universe does. in my opinion. But the other side of the coin is mathematics is a complementary but a very important part of that study. And I certainly enjoy the pure elementary number theory work, which, by the way, when you say elementary number theory, it doesn't mean as arithmetic you learn in grade school. It's fundamentals, if you will, of
a little more complicated than what you learn in
yeah.
elementary school.
Yeah.
And Dr. Rachel Traylor, one of my favorite guests from the Non Sequitur Show. How are you?
Oh, I'm doing all right. I've only been on once.
I know, and you're still one of my favorites. Well, you've been on that once, and you've been on this channel once too.
Okay,
so
that's true.
That 1 + 1 is 2, right? I have to ask a PhD.
Right?
Yeah, I have to ask a PhD in mathematics what 1 + 1 = 2 is, just to make sure that I'm right. That's
what
how
space?
pedantic I am.
Yeah. So which axioms?
Yeah, it depends what axioms you use.
And are these exact numbers or fuzzy numbers?
That's yeah. We can start getting a little. That's not nice. We'll be nice.
Well, before we do that, how about you kind of tell people about yourself? Because again, you've only been on twice, but by now most people kind of do know who you were, because you were actually a guest that people had talked about for a while. So.
Oh wow, I didn't know that. So I am a professional mathematician. I have my own company with my co-founder Jason Hathcock, and we essentially are private math professors. So we do research for hire, as well as some consulting on statistics, that kind of statistical analyses, that kind of stuff, as long as it's not any of the social stuff. I don't touch, as I tell people, I don't touch people shit. That means no social media analyzation, no surveys. We don't do that. We do stuff related to engineering, science, and technology. I got my doctorate at the University of Texas in Arlington, and before that, Master's of Statistics and a Bachelor's of Mathematics and Chemistry at Georgia Tech. And my field of interest is probability theory, stochastic analysis, and then from there, my research is pretty much like a spastic bouncy ball wherever it happens to go. Applied, pure, it depends on the day.
I absolutely love being the most dumbest person in the room. I mean, in this particular case, I literally am not even at a level that could even be having a conversation with these two people, and I'm thrilled to death to be able to do so.
But Rachel definitely is a real mathematician.
She's a mathematician for hire. How often do you find those?
Yes. And
more often than you think, sadly enough, now.
And boy, statistics and probability is one of those items that I didn't pay that much attention to in college, but it's now extremely important. And a lot of stuff. I also do a lot of work in cryptography, and random numbers is a really deep subject. And if you don't know how deep it is, that's because you don't understand random numbers.
It's a rabbit hole when you start talking about some of the stuff that I do deals with probabilistic dependency. So if I'm going to generate new types of random variables, you want to write algorithms to generate that. But one thing that we'll probably get to when I say this word is I have to prove to you that what I'm generating is what I say I'm generating when I write that code. And that's a rabbit hole to prove that it's, as a mathematician on paper, I can say, well, I'm just going to generate a uniform random variable and then create functions of that. But if we were actually to implement it, say I were to go to Landon, because he's probably a way better computer scientist and programmer than me, and we were to implement it, now he has to go, what does it mean to actually have a computer generate a uniform random variable, and how do we know that it's truly generating that random variable? That's a rabbit hole dealing with the computation side, and then we have the mathematical side of how do I prove correctness of what I've done.
So I'm known for this wonderful hack on the patent office called Lavaround, where we got a patent seeding pseudo-random numbers with the cryptographic hash of the digitization of a chaotic system. That's the title of the patent. And what that meant was we had at Silicon Graphics, we were pointing cameras at lava light lamps bubbling away and using that process to generate keys that would seed pseudo-random number generators.
I'm going to ask you a lot more about that if we don't have time to cover that on the show.
Before I do, let's drop it down a few notches. So,
Sorry.
To like the average layperson, including myself, because I didn't understand a word of that, and I actually took math. So let me try to kind of wrap my head around this, and maybe we can explain it for the audience. When you say that something is random, right? If you have a random number generator, when I used to program you always had to give like a seed. You didn't actually ever generate something that was truly random. Matter of fact, depending on what seed you had for the randomization, you could predict what it would be. So it was deterministic. But is there actually a way to make a program such that is a truly random? And I'm not talking about any kind of quantum stuff. Just using like assembly language or something.
Well, I think probably the answer is no. But the reason why we use the word pseudo-random is because it is not. It's a typically pseudo-random generators are some state machine, some very explicit algorithm where you start with this and you will get very deterministic values coming out of this sequence. And that's what computers are good at doing. It's extremely difficult to trying to make a computer spontaneous is not a thing, because computers are by design to do what we tell them to do. And if they don't do what they're told, we consider them broken. We send them out for repairs or replace them.
So in theory, how would you go about trying to get a computer to do something that is considered to be truly random? And again, if you have to dive into the quantum realm, that's fine too. But without doing that, is that something that you could theoretically do?
I know, Rachel, you want to take it, or want me to take that?
I mean, so I'll qualify the statement by saying that I am a purely applied mathematician, meaning I code as a necessity. So, take that with a grain of salt. To me, I say no. I would say it is not possible to force a computer to be truly random in the same way that we cannot, like I said, setting aside the symbolic language of Wolfram Alpha and Mathematica, even if we have a computer calculate, say, an integral, right, the area under some curve, an integral is a continuous sum, right? We can't make computers do continuous sums. We do a discrete sum and an estimation over very, very tiny, tiny intervals, and it looks close to an integral, just like your pseudo-random number generator will look very, very close to truly random. But I don't think we can truly hit that with a computer in the way that I can on a board declare, like, I can compute an integral, just fine, an indefinite integral or a definite integral. And what I've done is a continuous sum, but to make a computer perform that calculation, what's going on underneath is a discrete version of that.
Yeah, because if you're going to sum an infinite series, precisely that tends to take an infinite amount of time.
Is that like doing if I remember correctly, I think it was a Riemann summation?
Yeah, kind of right. Thing? So okay. Even,
I remember something from college. That's amazing.
So if you wanted to determine even, summing infinite series, first you have to determine if it converges to anything or not. And, from a computer standpoint, I would like to say that's why you still need, professional mathematicians, because there are things that we do as mathematicians that you cannot teach a computer to do. Mm-hmm. It's not possible. And then, as far as the randomness, that is something that has to be considered. And I actually ran into that problem in one of my own research projects, because I am trying to write one of those, and it's not working. I have proven the algorithm correct, as in, if you could program a computer to do this, this will prove that this is generating the sequence that I tell it to. But when it comes to actually implementing it, there's a difference between the proof and the implementation.
Yeah, we're going to definitely talk about that proof here in a few.
So one of the things, again, is computers are deterministic, and so what passes for a random function is basically a value, so we call some state, and a process to translate that state into another state. And it doesn't translate it into a random state. It's very deterministic. The next state is blocked. Like, you can test whether your pseudo-random generator is working, because you can say, if I have this value 5, the next value must be 7, given this state. That's not random. Another problem is that computers do not work with real numbers. They work with a limited set of integers. So even if you have something in your program called real, it's not real. It's an integer, right? It's a number and a times some exponent, typically, power of 2. So when you're trying to do these calculations on a computer, you're not doing the kind of calculations that mathematically you would want to do on an integral. You have to fake it.
Yeah, and that's why it's kind of like, I hate to use the word pseudo, but what is pseudo-random? I mean, I don't know how else to put it. It's pseudo-random, right?
It is pseudo-random. I mean, I think that's the best word for it, in the same way that, yeah, I mean, that's where my beef with the AI will solve all our problems thing comes along, is that computers aren't a substitute. Like, they're so limited, and they're just calculators. That's all. That's all they are.
Calculators.
They're fancy calculators, and there's only so much that they can do if they're going to work in, as Landon mentioned, yeah, you're not even in the space of real numbers, which in itself is pretty limited to deal with a lot of things. Mm-hmm. You're even more limited than that. So your real number, I mean, even at your approximation, if you type pi into a computer, or even if you call it, it's still only going out to a finite set of decimal places.
It obviously couldn't. Well, we don't. I mean, obviously, you can't calculate all of pi.
Right.
Infinite,
so I can manipulate pi on a board
sequence.
All I want to, and use it in proofs. And what I've done is fully correct. But if you have a computer do something, its calculations may end up, through propagation of error, being somewhat far off of mine that I do, on a board myself. And it's not because I'm wrong.
Mm-hmm. Right.
Now computers can also manipulate symbols. And one of the things that I was very important in my early development of mathematics was, I had exposure to computers back in the mid 1960s. My father also worked for Pacific Telephone.
Oh, I should tell you, Landon, then I found inside of a book in a bookstore around here an old IBM data card that goes at the end of the stack.
Oh,
just inside of a book on matrix theory.
Yeah. They make good bookmarks. But and I have a pile of those punch cards as well. But the thing that I got exposed to was because Pacific Telephone was part of AT&T network, we had on our farm a data terminal that was connected to the telephone network. So I never, people said, we do all that phone stuff. You ever go into phone hacking? No, I didn't need a phone hack. We had an actual terminal at our, on our farm that we could go and make and route calls through the network. And so getting onto the ARPANET in 74, I think is when I started. And I discovered at MIT there this machine called a Maxima machine. It was a Lisp machine that was doing symbolic algebra manipulation. And it was fantastic because the kind of the drudgery of arithmetic, of like long division and so forth, it could do on algebra and symbolic systems. So I could dive into and manipulate symbolic systems that would be impractical to do by hand, because you drop a minus sign someplace and it'll go in a handbasket. But there, for symbolic, you can say, I have this value called pi that has properties, and you can then use the mathematical properties. So there, you're working in symbolic space, which ironically, it's taking integers and representing them as symbols. But
even still, if you program it, you just use the pi symbol. I mean, the computer recognizes that for a specific. I mean,
yes.
I don't know how many things it's programmed to use it for, but I mean, it recognizes that to be equal to whatever pi evaluates to. I mean, it's basically going to give you some value that. How many iterations does it does? I mean, you have that symbol for pi. I mean, obviously it's not going to be an infinite amount. So, I mean, I use pi to like 5 decimal places for most things, right? But I used to know it to like 20. 3.14159265358979232 something or other, right?
Yep. So, but I mean, in symbolic algebra or symbolic systems, you can have it do, integrals, because it's got integral tables and it's got rules to apply, and it can do some extraordinary things in calculus that would take a human a long time to do, and unlikely a human would do it correctly the first time. And so I got to explore also differential equations and all kinds of things where I could look at a system, describe it mathematically, and then throw it at Maxima to do the churning of the symbols. If you will, I was doing arithmetic on symbols, literally.
A couple things in live chat. On one, by the way, yes, I do realize that my hair is green because of my green screen. It's just the way it is when I have low natural lighting in here, because a lot of my lighting is dependent upon the window that I have. It's kind of overcast, I guess, outside. But you know what? Just think of it as radioactive, as Landon had pointed out. So it's kind of a good thing for this particular, hangout is on nuclear stuff. But by the way, we will be having a presentation. I don't know, next week or maybe the week after, on nuclear power. Again, kind of similar to what we did before, only this one was actually written by Landon for, what was it again that you wrote it for?
It was originally for dental maths. It's going to be on discussion on nuclear weapons.
Yeah, nuclear weapons. Yeah, so.
Yeah, but just think of Steve's brilliance is so magnanimous that the particles streaming from his mind are going faster.
That's what it is. It's just like it's kind of like, you've seen a Van de Graaff generator, people, when you put your hand on it, it makes your hair go out. That's kind of what it is. So I have these charged particles kind of like emanating from my head.
Yeah, but he's got shrink off radiation coming.
I do want to thank I do want to thank Kyle for this particular layout. He made this, and I think this layout is brilliant. So props to Kyle. He's my co-host on Non Sequitur Show, Monday through Friday on the Non Sequitur Show. You guys haven't checked that out, link to that in the video description. And I did put the link to the DEFCON 1 Science channel in the video description. Again, until we get some subs, won't be streaming to there, but I'm going to be uploading as an archive to that particular channel. So
I hope to throw it back to Irrational and talk about sorts of symbolic algebra systems. I assume you work with things like Mathematica or Maple or those.
I do.
Maple Math?
Now, Maple I haven't done much with. Mathematica I have worked with, and I will say that it is at once indispensable and the most irritating thing.
LaTeX is confusing to me. I mean, I use it.
Oh, don't you dare say anything bad about that.
No, I use it. Okay,
this is a family-friendly show.
I mean, when you want to do things, make it look nice, then you use it, right? But sometimes getting it to look the way you want it to look, not so much as easy.
When you want to publish in a journal that has insistence on weird tech library stuff.
That is a service we offer, by the way. My co-founder is a tech expert. I would say I am intermediate advanced, but he is.
You do all the formatting for people?
We do. I mean, for our stuff, we've designed our own presentation templates, our own paper templates. We've done posters. We can do anything you want with tech. Yeah, but that's because we're super picky about everything. I mean, we're picky about that kind of stuff.
I have a paper coming up that's being published with a former intern, and I think what we might want to do is hire you to give you the tech paper and say, please borrow with this and make it, make it pure,
make it pretty.
We can do that. That's in fact what even we probably could do is, depending on the journal, we can edit or alter or give you a custom style file, so you wouldn't have to continually use us. You'd be able to just import the style file and it would format it for you.
Cool. Anyway, so back to stuff about these symbolic systems. So you've used this.
Yes. So for me, Mathematica is fantastic for exactly what Landon said. There's certain integrals, or if I'm exploring something, right, I can explore. Sometimes I explore by hand, and I do a lot more arithmetic for a professional mathematician than you'd expect, because a lot of it is really just, I hate to say playing around, because then people don't take what I do seriously, but that's what it is. I'm trying to figure out if a hunch that I have might lead to something. And so I can do a lot of that by hand on my whiteboards that are behind me, like right there. Yeah. And, but then sometimes, I make mistakes, right? I forget a minus sign, or I don't bring down. So being able to,
I got to tell you real quick, that was the biggest in nuclear power school. The greatest mistakes I would make was forgetting a stupid negative sign. And
you know what? I'm a professional and I still do it. So Mathematica, in that sense, if I need to just, all right, what is this thing? Please just evaluate it. Yes, that's perfect. Sometimes, though, if I'm trying to play with it, the way to finally get what I need in a certain form, say I want to simplify something, right? We've got all sorts of tricks in mathematics to get me what I want to do. Like, I can add one and subtract one, because if I add one, I have almost what I want, but I really wish I had a plus one. So I add one and subtract one so that I can group here, get what I want, and then there's a minus one over here, right? Yeah. That's a pretty classic trick. Mathematica is not smart enough to like figure that stuff out. So sometimes if you want it to say simplify even a rational expression, it gives you a bunch of like, okay, I can't use that. That's doing me no good. So I'd say I do like, I'm 95% by hand on the board, and then 5% basically Mathematica to basically check my work to make sure my arithmetic is correct. But I haven't been able to use it to do anything clever.
Well, even
like,
from
and
algebra is hard.
that's really frustrating about Mathematica versus, for example, one of the early systems, Maxima. You had full Lisp underneath it, so it's like the Emacs of symbolic stuff, and you could go in and build. I want to put stuff over here and take it over there and get that function put in.
Yeah, Mathematica is a pretty closed system, and not as definitely, you know, if you think tech is unintuitive, Mathematica is a programming language. You know, the function I would think to call for some operation does not do what you think it does, and they've actually named that something else. But
it makes really cool graphs and stuff. I mean, especially if you're working on 3D
for
stuff.
graphics and animations,
you can't beat it, right?
Yeah,
I've seen some of the stuff you could do on it. But then, like you said, I've looked at the language, and I'm like, oh, forget it. There's no way I could ever learn this.
I apologize, because probably watching this video as some Mathematica expert to say you just do da 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 da. But as I say, really what you want, what a mathematician wants out of symbolic algebra system is knobs to turn.
Yeah.
Right? You want to explore with.
So you want to make it like a basic thing and then kind of tweak it here, tweak it there, kind of thing.
Yeah. And so you got some massey equation, and you say, let me look and let me explore the derivative of that equation with respect to x, y, and z. Right, and so you can throw it at the symbolic system and have it do all that grind, and in a very short period of time, start working with the derivative in that respect, and start exploring that space.
Yeah, it's like having an assistant.
Yeah. Real quick,
exactly.
we got to get through the live chat just real quick. Then we're going to start moving on to proofs real quick. But I want to note a few things. Like Fred said, RNGs and computers are based upon CPU clock. That's why it's not truly random. That's how I learned it too. A lot of it was taken from it takes something from the CPU clock, and then you have a seed, and then it kind of builds it from there most of the time. I'm sure there's other ways of doing it. Back in my day, that's how it was. It was off the CPU clock.
Well, there are really poor systems. For example, let me flame Linux.
Don't you dare! This is family friendly here.
And let me flame Yarrow, the abortion that Bruce Schneier pushed out. None of those systems have been found to be cryptographically sound. Even the current ones, we can distinguish the output of dev random and Linux from there. And think about it. It doesn't matter if you're saying, well, I'm going to go and I'm going to grab these bits of the clock, and I'm going to grab the disk thing, and I'm going to grab the last time a packet came through, and other silly sort of stuff. You're just taking a whole bunch of variables, throwing them in a mix, doing a determinant.
That's why it's pseudo-random
with an entropy pool, right?
Right.
If you are really paranoid on cryptography, you first of all will doubt the measurement of entropy. When Linux says I have this many bits of entropy, really doubt and say, could you prove? Or in fact, the people who do this stuff, when we point out to them, no, you don't have this much entropy there, they'll go and they'll fix it and they'll do some other stupid thing, right? So
is that dealing with Shannon information?
Yeah.
Okay.
Yeah, and another thing about this random state is that, you know, if I had a cryptographic system that was doing something serious, like say deciding whether to launch missiles or not, I would use so-called entropy and a function if I were doing that, and I would use it only once. I would treat them as a one-time pad. Yeah. Entropy should be like, you know, you should change your entropy like your underpads.
Well, isn't that how quantum cryptography would be, where you have a one-time use, and that's why it's basically considered to be unhackable, because one, if you do infiltrate the system, it changes the bits of the system, so it alerts somebody, and basically all the information becomes unusable. Yeah. But it's one-time use. That's the key, right?
By the way, don't even think about using Windows 10 so-called crypto random number generator as well. That's even worse. In fact, we've shown them how to determine their generator. And
the key thing is probably nothing's foolproof. Again, unless you have I do think that a truly quantum system would be something that would be considered to be unhackable for that very reason.
The essence of law of random and that technology is that what you need to do to a computer is give it an external stimulus. You want some system which has some underlying physical properties giving you stimulus that you have to digitize, because we typically deal with digital computers and not analog computers. But you want external stimulus to drive a computer as opposed to letting the computer do it itself.
Gotcha. Nestic asked.
He triggered me, so.
This is what happens when Landon, one of the smartest guys on the planet, gets triggered. It's not a pretty sight now, is it? Nestle asked, question, is random number generation a chaotic process that is very unpredictable but deterministic nevertheless? So is random number generation a chaotic process that is very unpredictable?
No, it's not. I would not call it, I guess it depends on your definition of chaos, but I would not call it a chaotic process.
Yeah, I don't know why it'd be chaotic.
Just because you don't understand.
It's deterministic, though, because clearly if you...
Absolutely.
I mean, you can determine it, so...
Yeah. So it is a deterministic process. Now, what you might be wanting to do is do a simulation. Let's say you're sampling customers out of a large pool, and you want to minimize a so-called bias of your samples. So you might have a pseudo-random generator that's picking cards at random out of a deck, right? That is something which a pseudo-random generator can do well.
Seraph64 says, we don't generate truly random numbers with just a computer. We need an external input that we can truly generate random conditions. Like he said that quite a while ago, and I've been trying to get to it.
Yeah.
But you happen to say that too. So, and by the way, I believe he's I want to say systems analyst, or I know he's a programmer. Yeah. I know Seraph works with computers, so he actually understood like everything that you had said earlier.
But he is right, and that was essentially, even though we were hacking the patent office on lower-end patent, which, by the way, the company that went and filed our patent, they said it was the first time they've in their 75-year history that they submitted a patent with claims, and all the claims were accepted without question by the patent office, because it was so weird of using lava light lamps in cryptography. It definitely was a general patent. But he's right. What you really want to do if you want to have a computer be spontaneous is have it transform external input.
Yeah, he suggests that, he says, can't we get to 2 nanometer transistor chips for random numbers and let quantum tunneling do the work? Now, see, I'm old school too, but I remember like they used to say there's a limit. I think it was like either like 10 or 12 nanometers is supposedly the limit because of thermal effects and quantum tunneling. And now, I guess with new nanofibers and new nanotechnology, they've actually gotten it almost down to like 5 nanometer level or something like that, some ridiculous amount. But you still have the quantum tunneling effect. Now, 2 nanometer, quantum tunneling would be pretty prevalent, wouldn't it?
Yeah, but the difficulty in using these physical systems is how you measure them and how you encode them. So the tricky thing, if they have something like, they have a Hausdorff meter and the photon goes this way or that way, is that when you start looking at it in detail, there's a lot of variables you have to control in the physical process. To either
that's when you hire Rachel. She'll take care of all those variables.
And you want to hire a physicist.
I'm gonna say yeah, the field of mathematics is big enough that I've had that. Oh, do you do cryptography? No, actually, I don't. What I can do is work with a cryptographer because my specialty is in probability, but I am not a cryptographer and I'm not a physicist.
Well, let me ask you that. How different is math, do you think, and I know we got to get to proofs here soon, but how do you think math differ from like physics than it is from a pure mathematical standpoint like you do? You do more pure mathematics.
This is a family-friendly show.
not a big fan. Well, okay. I know you've already discussed how you feel like engineering, and I guess engineers do physics, But I seen a disconnect there between like engineers and mathematicians, and I know a lot of each, right? And obviously, I took some physics courses, but I can't remember anything about them. But the engineers seem to have a lot more simplistic version of understanding of mathematics than somebody who actually is a mathematician. Is that something that you would say would hold true most of the time?
I would say that it's a matter of a way of thought. So, for example, the engineers that I know are extremely good at, say, spatial reasoning, right? Working in 3D systems or making 3D drawings or all of that kind of stuff. And I'm very close to a lot of mechanical engineers. me in particular, I don't really think that way. I think a lot more abstractly, and it's very hard to explain why. In my physics classes, for example, in college, if it was taught by a physicist, I actually did poorly, quite poorly, because they'd give you some kind of physical situation and say what would come out. Conceptually, I did not naturally gravitate towards that kind of reasoning. Then if I go take a partial differential equations class and see fluid mechanics done in that matter, all of a sudden it's like, oh, of course that's what that does. But it's because I look at the equations and the physical process basically is, I visualize the physical process literally through the equations and how the equation interacts. I don't know how better to explain that.
So I don't have the ability to do that. I can't look at an equation and go, that's what it's going to look like if I graph it.
I can. Well, and some things you won't be able to graph, right? Some things aren't graphable.
I mean, unless it's like a parabola, like x squared, x cubed. Those I know what they look like, right? But beyond that, if you look at like some kind of function, there's no way I can look at it and go, okay.
So I'll give you an example of what it's like to kind of think abstractly. So I do stuff dealing with sequences of dependent random variables, and that notion hasn't been really formally talked about until very, very recently. And one thing we'd like to understand is not just that things depend on each other, right? We have physical systems and particles bouncing around kind of affect each other, right? We can create a lot of examples, but not just that they're dependent, but how are they dependent? Is there a structure to the dependency process underlying some of these, physical systems or whatever you want? I'm using physical systems because people seem to like those. And when I sat looking at them, both me and my research partner, we actually made an entire lateral shift. Is like, what if we just graphed the way they depended on each other? And when I say graph, I mean the way that graph theorists mean graph, right? So like what looks like a network, a directed graph or a directed network. And literally that lateral shift has precipitated 6 papers of studying the dependency in a totally different way by visualizing it. And I say visualizing because I don't mean like, it's not like graphing y equals x squared. It's literally moving into a totally different mathematical space to try to understand what's happening. And through that mechanism of my visualization, I can study and understand things. Whereas, I don't think an engineer or physicist generally is able to make that kind of a lateral shift that mathematicians tend to. But what they can do, and things that I personally am not as good at, is to take something literally in front of you, like an engine. Like, could I, literally, from physical principles, develop and build an engine? No, I don't think that way. I just don't. That's why people tell me I'm esoteric and useless, because I don't think in terms of things you can hold in your hand. If I work with an engineer, between the two of us, I think we can create something totally new, because I can move into a space that seems too abstract for the problem. But if I can bring it back to something they know, then they can take it and run with it with a tool they've never had before. I think that's the difference. I build tools, and I can build a great hammer, but I may not know all the great uses for it. An engineer knows how to take a hammer and build God knows what awesome things with it. That's the difference. It's not that they look at the world more simply and I look at it more complicated. It's just different.
Yeah. And I think one of the things to understand is just because you use equations in your job, that does not make you a mathematician. And it's sometimes what I find that's kind of sad is that some of the engineers I work with think they're doing mathematics. And if you try to say, well, we need to look at this mathematically, they say, well, I already done, here's the equations in my JavaScript, right? No, engineers have a really amazing capacity to take requirements and build function out of it. But mathematician, particularly when you're working abstract, it's a way of thinking, way of looking at the world. And the best analogy I would say is how an artist takes a composer takes a feeling and builds a musical composition to express that feeling. That's probably the closest analog to abstract, right? And if you ask the composer, how did you come up with this song? They really can't tell you. They just did, right?
I agree with that. a mathematician is far more similar to an artist or a musician than we're given credit for. There's a lot more creativity. Just because we are constrained by rules and axioms does not make us dry. There's a lot of creativity that goes into making something. Like, we make lateral leaps, right? It's a lateral thinking and a lateral creativity that makes a mathematician, as opposed to, an engineer that might live in a more constrained physical world. Now, it's not to say that they can't be creative. Obviously we have some amazing materials that have come out from scientists and engineers, a lot of times by accidents. Those are always the best ones. But yeah, as a mathematician, it's like constantly trying to compose something in your own head, and you don't even know what, you don't, it's not even like you have notes and you have keys and you have, some rules of classical composition. Oh, well, this is kind of what this is like a tonic mood or whatever. But there's far less restriction as a mathematician than people think. And it is far closer to the mindset of an artist or a musician than you think.
In that sense, when I look for interns, one of the things I also look in their resume is to see, are they doing something else? And if I see that, they paint, they write poetry, they play the guitar, those to me are very good signs that they kind of understand perhaps abstract thinking. And that's important if you're trying to hire a research intern.
Yeah, I play a little piano, a little guitar, but my abstract reasoning, I mean, I've always scored high on it, but I'm always amazed by, like, I think when Rachel was talking about how to think in different realms, different abstract things, like mathematics. You know how long it took me just to understand the concept of a complex number? Because I didn't relate it to anything physical, because it's it's not really on the XY axis kind of thing. I mean, it's kind of like a rotation around that kind of thing, and so you had to think of these terms and like that. It took me forever to get that concept down, and once I did, I was like, oh, this makes a hell of a lot more sense. I can't imagine going 3, 4, 5 different levels beyond that, and you're just like all these split octonians and quaternarians and all these other types of things out there that I couldn't imagine working within those realms.
What I've taught, and I've taught I've taught introstat, I've taught calculus, I've taught probability theory. I've taught some proofs, and the proofs are the hardest to teach because that's where the creativity and lateral thinking comes in. And linear algebra, actually, for engineers, when you start moving from calculus, that's very nice, and we can integrate things, to something like, say, linear algebra. We're going to start talking about abstract vector spaces. That's your first jump into the abstract realm. Mm-hmm. And that's why I actually came on that show that one time and did the stuff on Galois arithmetic. That's my way of trying to, if you want to know what it's like to think abstractly, it's like that stupid Frozen song that gets stuck in your head. You let it go. Let it go. Let it go of the things you can see. Let go of the constraints on one, meaning an object. Let it go. And as soon as I know that sounds kind of Zen and Buddhist and weird, but if literally you let it go. And once you can do that, that's how you can move to abstract realms. That's also why we get a reputation for being a little...
The only thing I took vector analysis. The only thing I remember was tip to tail. And I remember that two orthogonal vectors by the dot product is 0. Is that right?
Yes.
Okay. So I did take this, and I haven't done any research on this, so that was on the fly. But by the way, somebody asked me to rock out to Fur Elise. By the way, Fur Elise was actually one of the first songs I learned how to play on the piano. Beautiful song. If you ever want to play piano, learn how to play Fur Elise. Beautiful tune.
But here's the thing. I found somewhere as a kid that I just accepted the square root of -1 as this thing. And then I asked what properties it had. I didn't try to visualize the square root of -1. Same thing with infinities. Treat infinities as infinities that have interesting properties, rather than to try to count to infinity. Right? That's the counting to infinity is perhaps a important attempt in trying to understand scale. You might as an engineer, but as a mathematician, you've got to treat infinity as what it is.
Do you think most people try to do some kind of reification? They think of it as something more concrete than this abstract. I mean, like infinity. And again, I'm going to be way out of my depths here, but infinity is not like a real number on the reals. I mean, some people can say
it's something.
So it can't be treated as a real number. It can't be.
It's like perfection, right? We all strive for it, but we never hit it.
Yeah.
But it doesn't mean it doesn't exist and we can't sort of talk about it. just because we can't hit perfection doesn't mean...
Do you think actual infinities do exist?
Oh, of course.
Yeah.
Okay.
I mean, exist, but again, I'm talking to somebody who's very physics, engineering minded.
Philosophical person might answer different. So that's a kind of...
But if you said, are there an infinite number of things, physical things in the universe, the answer is possibly no.
Well, I mean, I got asked the other day, is space-time finite and infinite? And my answer is, and hopefully I got it right, but my answer is along these lines that, according to science, if Big Bang cosmology is correct, then the space-time is finite. However, philosophically speaking, it could be infinite. There's nothing wrong with an infinite regress in philosophy. It's part of the Munchausen trilemma. You're either going to end up with infinite regress or circularity or axiomatic assumption. I mean, you have to somehow have some base that you have to end up with. But correct me if I'm wrong, the universe, as I understand it, probably is more finite than infinite, right, Landon?
I mean, there's very good models that have us living very comfortably in a finite universe. A lot of cosmology does not require an infinite universe. Now, that being said, abstract sense, you have to ask, what do you mean by infinite versus finite? Is going around a circle and never finding the end of the circle a infinite process? In some ways.
If it never ended, I guess. I mean, like for example, I don't like having the beginning of the universe. I think it's a weird term to use, just personally, for the universe, right? Because beginning has a lot of connotations. But if Big Bang cosmology is true, then at some point when space-time, how it started, if it continued on indefinitely, just like a ray, right? I mean, you have a line that extends both directions, that's infinite in both directions. If you have a ray, you have a point that's infinite in one direction rather than like a line segment. Would that still be considered to be infinite if it has some kind of beginning but goes on for eternity? Would that be infinite?
Well, what about the positive real numbers from 0 up to positive infinity?
Well, same thing, either from the positive reals or to the negative reals. Would those be considered to be infinite? Because I don't see why they wouldn't.
The natural numbers are infinite, and it doesn't go below 0 or 1, depending on your definition.
Yeah, we had a big to-do on natural numbers the other day. Maybe you can kind of resolve it for us. 0.
I actually got into discussion with that via Twitter, and a lot of it has to do with the historical perspective of the notion of 0 being nothing. Because I said, if I'm going to index, say, a series and I start at 0, would you say like, oh, I'm running over the naturals or I'm running over the positive integers? Which are those two terms interchangeable? And the called the virtual math department that ends up happening on Twitter, I ended up revising my use of natural numbers and moving to positive integers simply from the historical connotation that natural numbers counted quantities of objects, and that's where that natural number came in. When 0 came along, we created integers. So I would say that you can define it however you want, but the convention usually natural numbers would start at 1.
That's the issue. Is that you said the word convention, right? By convention. Now, if you were to ask convention in Greece about 2,000 years ago, you might get a different answer.
That's right.
So if if you were doing an index for a summation and you're using n as to being the natural numbers, usually it'd be like n equals 1 to whatever, but you could actually use 0 and you wouldn't be mathematically incorrect?
Well, that's correct. Yes, as long as I was very clear when I say a member of the naturals, and then I might. So when I write a paper, because there are conventions, I mean, even for example, in statistics, it's convention that a capital letter indicates that it's a random variable. A lowercase letter indicates that this is either a realization of that random variable or a fixed point. And, like a Greek letter may indicate a parameter of a distribution. That's convention, right? We just defined it that way. Does it have to be that way? No, I could screw all that up and do whatever I wanted in a paper as long as I am very clear. So when I write things, because I don't know what backgrounds my readers have, because even in engineering, right? The letter delta in engineering, maybe that means a Dirac delta to you guys. That's the first thing that comes to your head.
When I see that, I think of delta, right? But I know it could be also used for
So
Lagrange, or was it Lagrange or no? Does Del is NAMLA? There's a whole bunch of different these symbols when they're arranged.
So when I write something, to me, we can argue about convention as long as I'm clear and I say, if I'm going to say, I try to go with the convention as is reasonable. If I have a reason to deviate from it, then I'm very clear. And even when I'm going with convention, if I say positive integers, i.e. n runs from 0, 1 to whatever, or natural numbers, i.e. n runs from 0, 1 to, as long as, I try to just clarify no matter what, because conventions do change, have changed, will change in the future. If someone reads one of my papers 50 years after I'm dead, and conventions may have changed again, then I would still want them to not go, oh, wait a minute, since this was written at this time, then this must have meant this. No, my paper should be clear at any point in time. So that's why I try to just be very clear. I define exactly what I'm saying.
What is actually it's used for too? What is delta actually used for other than, what are some of the things it can stand for? I'm trying to remember.
I mean, a Dirac delta function. So that's your, like a degenerate, infinite spike. It's used in, some statistical distributions to indicate the parameter of that distribution.
So symbols can be used differently throughout different things.
Oh, absolutely.
So and calculus has got a different.
Right. Yeah. In calculus, epsilons usually mean like something very, very tiny, but I can also use an epsilon to denote, say, a Bernoulli random variable. But, when you read a paper, the context will be clear if the author is very good.
Well, even
if still not, then it's
even okay, variables and constants, right? Okay, this is something that we actually had a discussion with a long time ago. Maybe again, you can add some input to it. Like, for example, take the quadratic equation, the general form. So ax squared plus bx plus c. The a, b, and c. Now those clearly are represent some kind of constant that you're times it by ax. However, those constants can be anything, right? They are in some way a variable because they're not something like a constant like pi. I learned a constant to be literally 2 is a constant, pi is a constant, things that cannot ever be changed. A, B, and C is a small
Steve,
letter.
when you talk about that quadratic,
those to me are variables. But
that quadratic equation we talk about as variables because you're trying to give the concept of the class of equations as opposed to a specific equation where you assign the variables a value.
But they're not signed, right? So I mean, they're not. The A, B, and C, are those considered for the quadratic? I've seen it both ways. Literally, I looked in the literature. I've seen them say that these are variables, and I've seen them say there are constants.
So let me see if I can expand on Landon's to help out with it. You've seen if I graph, say, the generic form of ax squared, we'll just take an easy one. We all know that general shape is a parabola. If I change a, it makes my parabola really skinny or really fat. So in that sense, the a can change, yes, but that constant, which can change, does not change the fundamental properties of the fact that it is a quadratic equation. It makes it skinny, it makes it fat, it makes it kind of somewhere in the middle. We can shift it maybe down, up and down by a c or over by some other thing. But the fact that it is quadratic is in that x squared bit. Sure. So that ax squared is giving me like Landon said, a family of equations. So is it a variable? I'll segue that into statistics and say that in general linear modeling, which does include quadratic, by the way, what are you trying to do when you are a statistician, right? You are trying to estimate those coefficients, right? X's are actually your data points. Spitting out some y, you've got some relationship in, say, 2 dimensions. And what you're trying to actually estimate is that linear equation, for example, right? We'll keep it simple. So in that case, when we say general linear modeling, we mean linear in the constants or parameters of that equation.
Right. Yeah, and even when you expand something out, even if you just have like ax, whatever, for like a binomial distribution, you have like ax1 and all that. But the a itself obviously represents a constant multiplier of some kind, right?
It is a constant multiplier in the sense that when we're discussing quadratic equations, the constant is just something that might change the shape but not the structure.
Right. Sure. And so when you repeat that formula in your paper, you are not saying that A is necessarily going to be changing, right? When you
Right. I get that, but the way, like I said, the way I learned a constant was literally that a constant never could change. Pi is like something that can never be changed. And somebody said in the real live chat, pi is not a real number. Pi is actually a real number. I don't know why they don't.
Yeah, it is. I'm sorry, it's not a rational number.
They said pi is not an actual number. Well, it is an actual number. It's not rational.
Yes, it is. Yes, it is.
But it's definitely an actual number, and it's transcendental. But I don't know why it wouldn't be an actual real number.
I think we settled that question a few hundred years ago.
Yeah, it exists somewhere on the real number line, between somewhere in the range of 3 to 3.2, it exists in that range, right?
Yeah, I'm going to address that. That gets to the notion, and I'm not, like I said, I'm not trying to make fun of anybody. That gets to the concept of limits, right? Just because you can't hit it doesn't mean the limit does not exist. So in this case, pi, I can create an infinite sequence of rational approximations to pi and never hit it because pi is an irrational number, and I'm trying to approximate it using rational numbers. That doesn't mean pi as a number does not exist. Doesn't mean the limit does not exist. Just because you, again, like perfection, just because you can't hit it doesn't mean perfection doesn't exist.
The way I look at pi, hopefully correct me if I'm wrong, but the way I look at pi is that it is a finite number, but it has an infinite decimal expansion.
It's not expressible given a base that's rational. It's not.
Yes.
Yeah. But what happens if it's a base pi?
Well, then I can change base. I can take a base that's an irrational number. So
pi to base 10. Pi to base pi is 10.
So you can't. But again, the way I think of these things is, if you just say 10, to me that's just a symbol. That's a numeral. That's just a symbol of something that represents something much greater.
But that's what digits are.
That's what I think all digits are.
They're coefficients of a polynomial that often uses 10 as the base. Unless you're doing computers, in which case it's hex or blah blah blah. But that's what digits.
I think maybe they might be talking about maybe some kind of Platonic realism, like Lamed says pi doesn't exist because I can't touch it. But some people actually do think numbers exist in some kind of abstract realm, right? If you're a Platonist, mathematical Platonist, I think I follow in what's called nominalism, but I don't.
Pi shows up in physics an awful lot. So it is a very real number. It's a very real concept, and it shows up in reality often. It's amazing how much it does, but it's a fun.
And correct me if I'm wrong, all real numbers, again, this is like what is truth. We're all like trying to sort these things out. All real numbers are a subset of complex numbers, right? Not a proper subset, but they are a subset, correct? Because I've had that discussion with a lot of people. They're like, no, that's not a complex number. I'm like, 3 is a complex number, right? 4 is a complex number. Pi is a complex number. These are all complex numbers because they're just basically a plus bi, and b is set to 0, so you're just taking the real part of the complex.
How many people have seen complex numbers basically as isomorphic to 2 dimensions, right? A complex number can be put on 2 dimensions, right? Your real and your imaginary axis. That's isomorphic to the 2-dimensional, right, Cartesian R2 that you know. Then it's pretty clear, right? A real number, say like 3, it is absolutely a complex number. It just lives on the x-axis in the complex space. So if you consider visually complex numbers to be similar to an xy coordinate in an R2 space, then that becomes a lot more clear. Now it's not literally a 2-dimensional. It's not R2, right? R2
is real. It's isomorphic to it, right? That's it.
Yes, structurally they have. I can map one space to another, but it doesn't mean that a complex number is 2 reals in a tuple. That's not the case. So I didn't mean to get pedantic on that, but I do say it's isomorphic to R2, but it can be visualized similarly to a tuple in 2 dimensions.
And R2, you just mean is a metric space that has 2 dimensions.
So it's a way to translate between the two.
Yes, R2 is that's your XY plane, right? Just R3 is it's your 3-dimensional, right?
So back to you say what you were talking about, the natural numbers. My convention I grew up with was that natural numbers started with 1 and went up. And the reason why that convention was, I had a lot of number theorists that would you make a statement, a prime number has only two distinct factors, in the natural numbers, one in itself, right? And you don't want to have zeros in there. So oftentimes it's convenient to have a set where 0 has special properties. Particularly if you deal with division and you want to deal with dividing by 0. So you'd have these you have this thing that would be 1 forward, and the convenient thing to call those natural numbers. Now, but I'm rare that there's other conventions where 0 is part of the natural number, which means when you write a paper, you need to say,
be clear.
Capital N.
You should define it every time so people aren't, confused. Because I know mathematicians love to break rules a lot, and they love to use their own kind of nomenclature. They love to abuse notation quite a bit.
Oh, wait a minute. I'm sorry. I think you're talking about physicists.
Yeah, physicists do
really?
that. Mathematicians sometimes have
that might be true. I see a lot of abuse notation, though.
Yeah, I'm sorry. I think you must be talking about physicists.
Damn them physicists.
Yeah, but not mathematicians. Oftentimes, the symbols, you have so many more concepts than you have symbols that you have to go and either reuse symbols or define your own symbols.
You know, Landon, I'll give him one, like maybe the notion of using one for, say like, multiplicative identity when, maybe the multiplicative identity, if we're in the space of matrices, is the identity matrix, but we might still, for ease, write it as one. Sure. If we say we are on the space of matrices. Maybe that's the sort of abusive notation you're meaning, because to you, one means one object.
Well, yeah, I mean, like 1 equals 0, obviously, that would be for the zero, what is it, the ring zero ring property, whatever it's called.
Well, yeah, if your multiplicative and your additive identity are the same, then you can write that, but that doesn't mean the number 1, as in one object, equals the number 0 representing
it's still really
0.
confusing to somebody when they see 1 equals 0, but they're not understanding that one is actually representing the multiplicative identity, and one is representing the additive identity, rather than 0 and 1.
The snark in me would say that unlike, the social media sort of consumption of media, you actually need to read the whole damn paper. To get the context.
Yeah, it's not something to easily wrap your head around. Again, I had to learn, honestly, most of things about real analysis on my own. I never took real analysis in college. Just nothing they teach you in nuclear power school. You don't need to know real analysis. They say this is how you do a derivative. This is how you do an integral. Go figure out calc kind of thing. I mean, it's all graphical calculus, so it's not even a lot of analytical properties. You start off learning how a derivative is by literally doing fundamental calculus and just saying this is the slope, this is your f of x of h minus x, that kind of stuff. It starts off that basic, and then they say this is how you need to think of a derivative, but it doesn't get into the real analysis of dealing with things like multiplicative theory and stuff, multiplicative identities and matrix theory. Although I did take matrix through Texas A&M, so luckily I learned that tangentially to nuke school, because they don't teach you don't need to learn matrix theory, and you have to learn about, obviously, integration, because you're dealing with the core, and you have a neutron flux density across the core, and you have to know where in that core you're going to have spikes of where you're going to have neutrons more likely to be absorbed by the fuel, more likely to be not utilized by the fuel and actually leaked out. Landon and I had a great discussion about this not too long ago on my channel if you guys want to check it out. But yeah, so that deals with integrations, and a lot of it is, especially like you mentioned about engines, the work cycle of an engine, right? You have a 4-step process. The bottom part, that work process, is literally the integral is equal to the amount of work done in the system. So there's this really, I hate to use the word integral, but they are integral. Physics and math, there's a strong correlation between them, obviously. Now, obviously, the physicists I've seen, like you said, the abusive notation has probably got a lot more than what you would find than a pure mathematician. By the way, I can't read the internal chat, so if you're sending me internal chat, I won't be able to see it because it'll change the whole layout. So if you have a message in the internal chat, I'm not seeing it. So if it was to me, I'm not getting it. I just see it pop up down at the bottom.
Yeah.
Was that to me?
By the way? So let's move on. So we have about an hour or so. Let's move on actually to the topic at hand, which is what is truth and what are proofs and that sort of thing.
Yeah, I mean, one of the things we had discussed before is what actually entails to be a proof, right? We all have done basic proofs before, right? Most people that have had math can do like the proving that the square root of 2 is irrational, right? Something like that, or basic proofs, right? But what does it actually entail to say that you have something that has been proven? Not this, you have an idea, not this conceptually it might work, but to the point where you can actually say, like, for example, a prime number is proven to be prime.
That seems a little... like a particular number that you're showing as prime.
Yeah. Or general, what entails a proof? I mean, we like I said, most people probably know how to do like a reductio or something, proof by contradiction, or even mathematical induction. But
I think what the place to start is to recognize that, unlike philosophy from the small amount of understanding of modern philosophers, is when we as mathematicians prove something, there's no middle ground, right? It's either true or it's false, right? A statement is either true or a statement is false. You cannot have a statement that is both true and false, or neither true nor false. We don't accept that.
Those are basic classical logical things, the law of contradiction.
Right, like I said, like leaving the philosophy part out of it. So then, there's a reason that mathematics is the only field of study that has never been reinvented, but only built upon, right? What was true in mathematics 3,000 years ago is still just as true today as it was, although our, say, theories in chemistry have been revised, and physics especially, several times. I mean, you've had physics revolutions, classical to quantum mechanics and that sort of thing. I think the thing, if you're going to ask me, and there are lots of formal definitions in books on mathematical logic and usually in proofs books, but to me, to keep it simple, it is basically a series of true logical steps that demonstrate the truth or falsehood of another statement, of an indicated statement that you're interested in. So
given a set of axioms.
Yes, given a set of axioms. So, if you're trying to prove that, say, the square root of 2 is irrational, that's a proof where you're trying to show that something in particular fulfills a definition, right? Then there's different flavors of it. Now that one, you're trying to prove that something meets a certain criterion and fulfills a definition. So first, what is the definition of an irrational number? So if you have a bad definition, and then this is true in mathematics, you have a notion of what it means to be well defined. That in itself has a definition. You can't, as creative as we get to be as mathematicians, you can't just make something up and say, I'm going to build a whole system on it. There are criteria you have to make sure that you're dealing with to ensure consistency and well-definedness of what you're trying to do. In other words, I got to fit in with other concepts in mathematics. I can't just go create something totally new and say, well, I broke mathematics, you're all wrong.
You have to work within what's already been existing, right, in some degree.
Well,
unless you're creating, there's constructive math, but I mean, for example, if I'm working with, like you said, irrational, I have to use the definition of a rational number like everybody else does, right? And the way, correct me if I'm wrong again, the way I learned it was basically a member of Q is equal to a P over Q, and I mean Q as in like the set of all rational numbers would be, you have to be able to express it in a form of a ratio.
But wait, Steve. Really, what you have to first of all, you have to use a well-defined. Your definition should be well-defined, right? Mm-hmm. It's nonsensical and paradoxical, so-called, or contradictory. Is not going to do
a well-defined formula.
If you want to communicate with other mathematicians, you want to use common language. So it is possible for you to have this thing called irrational, define it in a completely crazy way, and as long as it's well defined, so what? But when you then have a conversation with someone else and you say irrational, you're not going to be saying the same thing. You're going to be talking at cross purposes.
So when we say well defined, that it has an actual definition. In logic, it would mean that the logical statement or the logical thing you're creating is unambiguous, as in, like, philosophy and colloquial language, we allow interpretation. If Landon says it's cold and I say it's cold, the actual temperature in the room may be totally different, right? It's our interpretation. I get cold maybe easier than Landon gets cold because he goes to the South Pole. So, and I, lived in Texas. So he gets cold at a lot colder temperatures. So you can't trust either of our definitions of the word cold. Whereas something like, say, a rational or an irrational number or a random variable or a measure space or any of these things have unambiguous definitions. It doesn't matter who looks at it, who reads it, who says it, who writes it. The definition does not change. And from an equation standpoint, if it helps, one other way of looking at it is, if I want to interpret it as a function, for example, a function is well defined if the form of my input does not change the answer. In other words, if I plug in 1 over 2 and I plug in 0.5, right? Those are equivalent expressions of, a half. One's in decimal form and one's in, like a rational form. I shouldn't get two different answers out of that, right?
There should be there's always a one-to-one correspondence with a function, right? For every one input, you get one specific.
So if you put in 0.5 and I put in 1 over 2 and we get two different answers out of that function is not well defined.
But even 1 over 2 is well defined. I mean, what a fraction is still well defined in mathematics, right?
There's two layers of meanings we're talking about here: the logical notion of being well defined, that being unambiguous, and then functions or metrics or other mathematical objects being well defined. So there's two layers that I'm kind of giving you the definition of here. So well defined is used in both cases, and we're concentrating on the logical, unambiguous, but it does translate to even a function or an object's well defined as being unambiguous with respect to input.
Do you want to add on that real quick, Landon?
I mean, I'm thinking as well that well-defined has a formal definition in formal logic.
Yes.
But one of the things in particular, again, that the property well-defined is that the mathematical properties are the mathematical implications can be understood independent of the mathematician. Right?
Yes.
It's not as if I've got a vague concept about complex numbers and we happen to share that same vague concept, so we have the same vague. No, it's a precise.
Unless you're an engineer, because they would use like J for complex rather than I.
Yeah.
Because I stands for concurrent. So
now there's a difference between a well-defined, something being well-defined and the nomenclature being common, right? The notion of what an integer is well defined. The term natural number might have some ambiguity depending upon context.
Well, it's still well defined, as you said, based upon your axioms. If you start off with the natural numbers being the countable number ones on up, 2, 3, 4, 5, then you still have a well defined system, don't you?
Yes, it's still well defined. And then of course, if I want, so first, I can't prove a statement that's not well defined. So I can't prove, let's take an example. Starbucks makes good coffee. I can't prove that to be true or false. It's impossible it's not a well defined statement. Starbucks makes good coffee.
And that's one of the reasons when
I think
we
that's
talk
an
about
objective fact of reality, though.
Sure, but in physics.
Wait. Hold on, Steve. Are you actually saying
I'm not a big fan of Starbucks makes okay coffee, but I've had much better coffees from much smaller breweries.
Yeah, you have to come to Espresso Central at the place I work at.
Starbucks is mass
espresso.
Yes, Starbucks is one of those.
For that.
Yes, it's one of those mass-produced things that it's kind of like McDonald's. Starbucks is like the McDonald's of coffee.
But look at this. This is an example where we have some mutual understanding, but good coffee is not well defined. You can't mathematics.
But my sponsorship with Starbucks has now went to hell. So thanks very much.
So in that case, because people will come like on a more serious note. So let's take something a little more serious. Someone might come to me and say, "I'd like to do some stuff on social media analytics dealing with influencers, for example. And I want to insert all of these complicated mathematical tools or whatever. Can you help me?" And I outright denied any involvement with that. I don't care how much money you pay me. No, nothing is going to get me to work on that. Why? Because nothing about that is well defined. There's nothing I can do for you to help prove that this person is influential on social media and this one is not, because that's not well defined. Define what it means to be influential. So, and that's a more serious note, because there are companies kind of live and die by that whole social media influential crap. There
are some metrics you could use to make some kind of fuzzy kind of things, couldn't you?
That's true. And that's where, a statistician, I think, internally has a Hippocratic do no harm sort of oath. So if I were tasked with dealing with this as part of my job, one, I would probably quit. And two, if I were, you put a gun to my head, what I would do is I would say, okay, under these constraints, what I would give you is an estimate to be used, but I would say this is not for quantifiable results, right? This is descriptive at best. I would never allow that to be used for any kind of quantitative decision, because that's not well defined. But you can see now how trying to apply mathematical tools to, if you don't start with a well-defined statement, at best you're talking about junk. At worst, you can have some pretty serious consequences to applying mathematical tools to something bad to start with. So you have to start with something well-defined.
So this is about proving. In physics we say we don't prove the theory of general relativity.
Right. No theories are improvable.
And there, from a mathematical standpoint, physics has to deal with things that are not well defined.
Yeah, that's a good point. I haven't really thought about that, because you're right. I mean, things like you can express general theory of relativity, obviously, using field equations and things of that nature, but you're never proving that general relativity is the way reality is. I'm a scientific instrumentalist, although I do kind of like model-dependent realism. But I don't think that a theory has to necessarily be the way reality is. Matter of fact, I don't think there's any way to determine such a thing. I don't know how you'd begin.
Reality has no obligation to obey your theory.
Yeah, so like general theory of relativity is just our way of describing what we observe of reality. Whether base reality is like that, who the hell knows? We have epistemic limits. There's no way we can know such a thing.
But if you're being honest about physics, you make use of well-defined mathematical properties to try to express something.
Yeah, and then if you don't, you throw in fudge factors.
Which hopefully has some basis in reality.
Statistics you see it in statistics as well. So, for example, everyone likes, say, the central limit theorem, right? If I standardize my variable, then it's approximately standard normal, and I can start using z-scores and all that crap you learn in Stat 101.
T squared, chi squared, chi, chi.
So the thing about that is...
ANOVA. God, I hated that stuff. I hated it.
That's good. It drives up my salary.
Yeah, let her. Hey, so there you go. If you guys hate all that statistic stuff like I did, there you go. Dr. Rachel Traylor, she'll do it for you. Work out some negotiation. Give me 5% or something for the brokerage thing.
Finder's fee. Yeah, brokerage is fine.
Yeah.
But the thing is, if I'm dealing with real data, can I prove to you that something is normally distributed? I can basically use, say, there's lots of statistical tools I can say to go, this looks very normal, enough for me to justify using this tool. Can I prove to you that data is normally distributed? No, I can't. That's where the judgment part of statistics comes in, is like, well, I've run a likelihood test on, say, a sample density or whatever tool you want to use. And it fell within the critical region for me to acceptably use this simpler tool. That doesn't mean I've proven that it's normally distributed. So in that sense, a lot of data analysis resembles physics more than mathematics. Excuse me. My dog is Koshi. My dog's name is Koshi, and she's whining at the neighbors.
Koshi, like,
of course.
Koshi is really like a Koshi.
And then the littlest one is Berlioz, because
excellent.
Koshi and Riemann
I tend to name my machines after physicists who happen to be also excellent mathematicians.
My dog is named Dedekind.
Oh, nice.
I'm kidding. That's a joke. I don't have a dog.
I have a cactus garden, and all of my cacti have names after mathematicians as well.
Yes.
But anyway, so this, and it's not to say that like physics or data science is inherently flawed because you cannot prove things that you're doing, but there needs to be recognized as, no, this isn't mathematics. Mathematics proves things. Mathematics creates tools, provably good tools, but physics or data science or something like that uses those tools, and you can't use the word proof in those contexts. And it's okay. We can still do great things with those fields, but we have to acknowledge what it can and can't do.
Just because you cannot prove relativity correct doesn't make it wrong.
But
correct.
What would it mean to actually prove? Again, like, for example, like Nan and I were going to be talking about, hopefully one of these days, even though we never got to it, and it's a little bit out of my depths, but like the pi being a normal number, how would you go about proving whether it's a normal number or not? And how would you know that you proved it?
Well, I mean, you want to know that pi fits the criterion, fits the definition of being a real number. So you look at pi and you look at its mathematical properties, and if it satisfies the mathematical properties of being a real number, you have proven that it's a real number.
How do you prove it's a normal number? You have the distribution of the...
Wait. Whoa. Pi is a fixed constant. It doesn't have a distribution.
But the distribution in pi for the way the numbers...
You're referring to the digits.
Oh, you mean the
digits itself
sorry.
in pi. The normalization of the digits based on your base.
Is that a theorem? Do people assume that that's normally distributed?
I don't know. From what I understand, they haven't determined whether it's a normal...
It's not been proven that pi is normal. There are...
Why is it so difficult?
There are a lot of heuristics to suggest that it might be, but has not been proven.
Well, to me that falls in the same category of if I've been given a whole bunch of data and I want to say, oh, is this normally distributed or not? Unless I generate it from a standard normal distribution, you can't prove it for sure. You can only say it approximates it well enough for me to use it.
Is that what makes it so difficult because of that?
Yes.
Okay.
Because when I'm given data, I don't know. I'm not starting with a well-defined statement. I'm starting with a pile of data, and I don't know what it is. I don't know what I'm given. So I try to find what is at that point, to me, data science, physics, engineering, those use tools of mathematics to do things. Data science uses tools of mathematics and statistics to do things. Okay, I would like to use the normal distribution tool, mathematical tool, because z-scores are really, really convenient, and I'd really like to use that critical region. But I need to justify that tool is the appropriate one, just like an engineer would justify the right kind of torque wrench, for a design. That's the difference. So in that case, the situation that you're describing, I think that's more on the side of like a data science of, is this the right tool to use to study the digits of pi?
Gotcha.
For example.
So normal theory, by the way, Steve, start off with mathematicians coming up with a well-defined definition of normal.
Yeah, what is a Gaussian distribution?
And some of the first normal numbers were numbers that were artificially constructed based upon the definition.
Right.
Once they had a well-defined definition, you could then construct numbers that were then normal.
Well, the way I understand number construction would be from a Cauchy sequence. If two Cauchy sequences, or if it converges upon whatever it converges upon, that's what the actual number would be.
Yeah.
Something along those lines.
Yeah.
I've done it before. I've actually, a long time ago, I've worked with somebody and explained how the proof works to see if a number is a real number by using Cauchy sequences.
Yeah, and sometimes in proofs you would sit there and say, all numbers of this form have this property, and all numbers that have this property are this form, and this particular number has this property, therefore it is of this form, right? It would be so. For example, a lot of times when you do primality tests, what you say is, here's a number. All prime numbers have this property. This number has this property. All composites, non-primes, do not have this property.
So once you've well-defined the properties, then you determine if that fits it.
Yeah.
Yes,
the property has to be well-defined.
Right. So things like rational, or that's well-defined. Things like, let's see, what else would be something? Real, transcendental, complex. Those are all things that are going to be something well-defined.
A metric space, right? I'm trying to create a new measure space, and I want to show that it fits the definition of a probability space, right? We can move beyond just like types of numbers. I want to show that this is a vector space. I want to show that this is a linear space. I want to show that this is a directed graph. I want to show that this is, there's lots of different, I want to show, and that's just fitting definitions, or I want to show that this is isomorphic to that thing, right? There's a definition of what it means to be isomorphic. I show that these two things fit the definition of being isomorphic, right? So it's beyond just numbers.
Yeah, if we start talking about bijections and surjections and all that kind of stuff, I'll lose it.
Well, that's exactly what it means to show an isomorphism.
I know, but I tell you, I know, but that's why I'm like, once we go down that rabbit hole, my brain just turns to mush.
But here's the thing to consider what it means to do a proof. And this was something that, number theory, fairly high-powered number theorists were sitting around and debating. When it's said that I discovered a new Mersenne prime, what really happened was that I constructed a proof showing that a particular number had a property that if and only if it has this property, it is prime. And so I constructed the proof. Although the proof I constructed involved a computer performing arithmetic calculations.
Yeah, that's a hot topic.
And
why computer proof?
Wait. There's more that was done, and then I made a claim, and another mathematician independently went and constructed a proof, and came up with the equivalent answer, and then a third mathematician independently constructed a proof, came with the answer, and independently, and then the consensus was that my original proof was correct.
But there's some controversy on computer proofs, are there not?
There is controversy on that. That's true.
Well, and again, the thing that you say is that the calculations that were done as part of the proof was accepted, right? So the proof was actually relatively simple, as it was Lucas sequences, right? The calculations necessary to carry out it is different than the proof. The proof is actually relatively simple. The calculations required lots of computer time, but the consensus is that my proof is correct.
Yeah, I mean, obviously it was accepted. I mean, you had like what, 8 world records?
Yeah, but that's a question about so the logicians. I mean, ironically, one of the people that found early prime numbers, D.H. Lehman, was a guy named Robinson, who was a very outstanding logician, and he was saying, well, in a formal sense, that number has not been proven prime, but in the sense that the majority of the mathematics departments accept the proof as correct, you can colloquially say that it's been proven.
That makes a lot of sense, actually.
Right? And so he was saying, and if you're dealing with colloquially, statements that are accepted by the vast majority of math departments are considered to be correct. But the number of people who have gone through and proven things may be relatively small.
Well, we're going about 90 minutes here, so
I'd like to just jump in a little bit to address that. I'm willing to step in the realm of controversy a little bit.
Ooh, this will be good. She doesn't normally do this, so pay attention, people.
The notion, and it actually, this kind of it was born of something that came across my Twitter feed of Mathematician of all people discussing a proof as a story that you give appropriately qualified people that they accept. And I will admit that my stomach was kind of just in this gut, angry, I want to lash out quite irrationally sort of thing. Because there's a lot of consensus does not make a proof. It's not a story. So for example, the 4-color theorem has had at least 2 or 3 very famous incorrect proofs. Mm-hmm. And they were accepted by consensus for a little while until someone found a counterexample. Mm-hmm. And so to me, when we discuss a proof has, and this is getting somewhat philosophical, but not inappropriately so, a proof has inherent truth. It doesn't matter if only I have proven it true and no one else believes me. Your belief in my proof is irrelevant to the truth or falsehood of my proof. So yes, it's objective. And that's the reason that I went into mathematics, is because it is the only objective field you can go into. It is the only thing that is truly objective. Now can I make an error in logic? Absolutely. But again, that error in logic is either true or false, and shows my statement to be either true or false, right? There's no, a proof is a series of logically true steps from one statement to another.
Let me approach it this way with you, if I may, because again, I know you're not a big fan of philosophy, but to correlate to philosophy, knowledge is something that cannot be false. Knowledge has always got to be true. You can have mistaken knowledge, right? You can think that you had knowledge when you really didn't, but something along the lines of a proof. If something is disproven, that means it was never proven to begin with, right?
Yes, I agree with that statement.
Okay, because that's why I think of proof and knowledge. It's called the principle of attribution and retraction. Belief can be wrong, right? If I think that I believe something and then tomorrow I find out that it wasn't the case, I just say that my belief is wrong. I mean, I was wrong about my belief. It can change, but knowledge, you can be wrong about having it.
You can change your belief, but knowledge is...
Yeah,
I agree.
You don't say that yesterday I had a false knowledge. You can say yesterday I had a false belief, but you once you get the actual truth, you go, okay, I just didn't have knowledge to begin with. And I think proving is the same way. You can't disprove something that's already been actually proven. It's not possible.
Right. If I create a counterexample to your argument, you now have been shown that your proof was not actually a proof.
Exactly. That's the way I look at it.
Yeah. Yes, I agree with that.
That's why they talk about things considered correct as opposed to they've been proven.
Yes, and I will give that credit to regarding the computer-aided proof controversy, because there's a lot of issues in, well, are you sure that the computer calculating something is really calculating it correctly, because they're not quite as good at calculating as you think, as Landon has taught me. And so that's where it would come in. It's considered correct, but that's where the controversy comes in of, my advisor, for example, is a purist and would say that any computer-aided proof is not a proof, no go,
because there's
not
no way
even
to possibly verify it properly? To see if they've had any error? Is that why?
That's some of the problem with the computer-aided proofs is, for instance, if you're dealing with, like Landon does, with very large prime numbers, if I were to independently verify that, right, to see if the computer was correct, I don't think I'd finish some of those calculations in my lifetime in a lot of cases.
Ridiculous.
It's impossible.
Yeah. So there's a case where what you need to do with a term called experimental mathematics is to have a number of people independently attempt to reproduce your calculations.
So now you're moving more towards like a physics or a chemistry.
But now you're just saying
appeal.
You're just saying that a group of people are by consensus at this point.
Well, isn't that what a chemical experiment is?
Right, but that's not. But a proof isn't by consensus. A proof is by the fact it's proven.
And that's why when Landon said, like, if they come up with a result in experimental mathematics, they would say it is considered true. They don't say it is.
Okay,
true.
but how about what about things that are so complicated? Like if I remember the Poincare conjecture that he actually tried to create. What was the Italian's name? The mathematician. You guys may remember. I don't remember his name. But he actually had to create a new field of mathematics based on Ricci flow to describe the Poincare conjecture. And so there's only probably, 5 people in the world that can understand what the hell.
But that's a proof. Just because you don't understand it or whatever.
But you're relying on them saying. You're relying on the expertise of 5 people that say, okay, this is proven, right? Because how long would it take to learn that kind of math? It would probably be quite. I mean, just looking at it, it brings tears to my eyes.
So, legitimate point that and that is something that, as a mathematician, I consider. I do not use any statement in a paper or in one of my proofs that I have not independently verified for myself. So, I don't take anyone's word for it. So, in other words, if I invoke, say, a theorem from, I don't know. I mean, yes, there's some like the fundamental theorem of calculus, but again, I don't invoke a theorem unless I could write the proof for you myself, right? Not a memorized recitation of it, but I mean, I can explain to you.
You want to have enough detail on it that you can do it yourself each time.
Some people work that way, some people don't.
You don't do that each paper, right?
To avoid that internal conflict in me of I don't believe what I've been shown just because it's been published, I independently verify everything, and I won't use anything that I haven't independently verified. Now, you can operate the same way, or you can take my word for it. It's up to you. But
you won't put that in the paper, right? I mean, you don't need to derive the fundamental theorem.
Oh, no. I won't derive that. I can say by the fundamental theorem. But again, what would happen implicitly is if I publish a paper and I put it out there, you are and should be free to come to me and be like, I have a question about that line in your proof. Gotcha. How'd you get from step 5 to step 6? And if I can't fill in those gaps except by appealing to someone else's stuff,
you've missed.
I'm not comfortable with that.
No, I think that's great. Actually, I think that's detailed.
And that's so. There's a case, for example, with regards to if you use something like Maxima or Mathematica in part of your work, you have not gone through the equation manipulation, algebra, whatever to do that. But you should at least understand the and have worked in that field enough to say, if push comes to shove, I can go through the drudgery of doing all this work.
See, I'm one of the people I learned it once and forgot about how to derive that stuff. I mean, obviously they teach you how to derive that stuff, but you don't use it all the time, so you just gotta accept it as true. You do. Well,
so for me, I actually like Mathematica helps me explore. But I am that person that even in an appendix of my paper, I put all of it. I mean, I put every single line. Now I'll put an appendix because it gums up a proof and it's not illuminating as to, the structure of what I'm trying to develop. But when it's like, I would say, okay, well, by say lemma A.2, I can make this simplification. And in the end of the paper in an appendix, lemma A.2 is me doing those arithmetic calculations.
So people can go validate it if they wish to.
Yes. Now I will expect that that if I subtract one from both sides that I can do. I'm not literally
right. There's certain mathematical things you have to take that everybody has some kind of basic understanding of.
But for me, if I want people to use the tools that I'm creating, they have to be able to trust them and not just trust them because I have a fancy pedigree, which I don't, or whatever.
Yeah, she does.
You can verify it for yourself and I'll back it up. You call me up to a board and say, I want to know how you did this proof. And I don't need the paper in front of me. I can do it. But maybe other mathematicians don't work that way. That's how I get around the notion of like, well, you're appealing, you have to trust this person. Like, no, I don't. I verified it myself. Yeah. And so I only trust my judgment.
That makes
and
a
you're
lot
free
of
to
sense,
question
actually.
it. we can have an argument. But the nice thing about mathematics and proofs is that if you and I have an argument, you disagree with the way I got from step 5 to step 6 in a proof, and you and I have that argument, at the end, one of us is going to be right, one of us might be wrong, but in the end, both of us will know the truth.
Mm-hmm. And that's what this hangout was all about, the truth.
And that's really the thing. So, in the case for in number theory and doing, computational mathematics, it was, sitting in D.H. Lamer's office and having him explain the quadratic forms, and having him explain Lucas sequences, and took me through the whole thing from beginning to end. And everything is logical. Everything is well defined. Everything is quite precise. So in that sense, I did the work to understand, a Lucas-Lamer or Lucas-Lamer-Reisel test. The fact that I use a calculator to go and perform some calculation steps does not make a proof, but it produces a result that's commonly accepted.
Gotcha.
The underlying theory is solid.
And like I said, we're fast approaching going to be the 2-hour mark, and then obviously I have to call this to a close. But in the live chat, if you got questions now, go ahead and ask them. And also, if you have some suggestions of what you'd like us to talk about, because we're going to be in future episodes doing various things relating to science, relating to math, relating to physics. We're going to be all across the board. It is a non sequitur type show, so we don't have a set format about what we can talk about. That leaves us open to talk about many different things. But what you guys may want to see, like I said, maybe the next time or the one after, we will do a presentation on nuclear weapons. I'm really looking forward to that one because obviously I like nuclear stuff, and I like things that blow up. So that works out really well. Now, again, I'm not advocating the use of nuclear weapons, okay? No, don't use nuclear weapons, but I do like how they work.
Nuclear weapons are bad, okay?
They're bad, but they're cool.
So that reference?
Yeah.
Yes. So what does it take for a mathematician to make a conjecture?
I guess, can you qualify as in like what goes on in my head?
You're going to publish a conjecture, right? So it typically is something you haven't proven. When is it reasonable to right? So you haven't proven it.
Right.
But you think it might be true. Now, correct me if I'm wrong, a conjecture is an unproven theorem, but are there such things as an unproven theorem? Because I've heard the term, I've heard the term colloquially, unproven theorem, but that basically means a conjecture.
Yeah,
so it's not a real term because all theorems are by definition proven.
Yeah,
right?
I would say that conjectures are
so it's
statements that are as determined. They are not determined true, but they are like we have a really, really, really strong hunch that it's true, but we can't prove it yet.
Yes.
But is that when somebody says like an unproven theorem, is that
no? It's not a theorem. Yeah.
If I'm in the middle of
colloquially bantered about, but because they mean a conjecture.
Yeah. If I'm working on something, I will say that I have if I haven't proven it yet, and I'm pretty sure it's true, I'll call it I have a proposition, or I'll call it maybe even a math feeling. I have a math feeling about this one. Like I'm pretty intuitively sure it's true, but until it's true, I can't call it anything quite that strong.
But I think in a conjecture, you can lay out a line of argument and reasoning, which while stopping short of a proof, suggests that should someone be able to complete the reasoning, the answer is probably true.
So I've never actually put forth any conjectures of my own. I try to, I try to prove them, but it is actually bringing up a decent point because there are some things that I've been working on a while that I've got conjectures on. In other words, I have a line of reasoning that I think I would go about to prove it, but I just can't fill in the gaps just yet, and I don't know why.
And an example of conjecture, perfect numbers. Natural numbers whose the sum of their factors less than themselves equal themselves. It is conjectured that there are no odd perfect numbers. And in fact, there's a whole subspecialty in elementary number theory about that. And you can make some very strong heuristic arguments that perfect numbers do not exist, but it has not been proven.
But are those just conjectures based upon all these years of observations that they think that, hey, this is what we see, so it's probably true?
No.
Or is there mathematical reasons why?
You'll usually have a reasoning, like we can lay out a bit of a heuristic, like if maybe this thing were true that I haven't quite proven yet, if this middle thing were true, I can finish the proof, but I'm not sure if this middle thing is true. It's like the gaps haven't been filled in.
Mm-hmm. Yes.
So
and you could give a heuristic argument as to why that gap might be a gap that's bridgeable.
Isn't that what happened with the Poincare conjecture? They didn't have that gap that bridged certain things.
Yeah, or even like some false, like the false proofs of the four color theorem. You know, they did actually teach us an awful lot about graph theory, and a lot of the conjectures may feel stronger because people have kept trying to find a counterexample to prove the statement false. And the longer people fail to find a counterexample, the more we kind of get a stronger math feeling that it might be true. It doesn't mean that it's true,
what is
though.
The significance of that, though? Let's say there is a proof of the four-color theorem. What is the significance other than, yeah, you got some pretty colors and maps and stuff like that? But what's the main significance?
Coloring in graph theory can have a lot of implications in scheduling, logistics and scheduling. So one example of colorings of a graph might be if I have a set of chemicals and I know that certain pairs cannot be shipped together because they'll make things go boom, and that's bad. And I need to figure out how to ship in the fewest number of shipments all of these chemicals to the same place. You can use vertex coloring to create to find the minimum number of shipments.
That's awesome. That actually makes sense to me.
Graph theory is super applicable. All these things this is an example of something that seemed really abstract and has a lot of powerful implications.
I would have never thought about something like that. That's why she's a PhD, by the way.
That one might be an interesting topic because graph theory is very approachable. Like, it's very visual. It's very there's a lot of applications in logistics, telecommunications, network engineering, manufacturing that come out of something like graph theory. So yes, the four-color theorem is not just a useless. We're just playing around with coloring maps.
I couldn't even color the lines anyways as kids.
Yeah. So in that sense, again, there are. It is funny when you deal in some of your philosophical shows or some of even your dumpster fire shows.
We don't have any dumpster fire shows.
What I hear that happens sometimes is someone takes a statement like proof, or you can't prove that, and then therefore derives all this truth from it. Mm-hmm. And they live in what as you call a state of mathematical sin, right? And that meaning that if someone says, well, you can't prove it, therefore this must be true, like physics can't prove quantum mechanics, and therefore right? You're using terms, well-defined mathematical terms, abusing them in a space that they're not meant to.
Yeah, and you also got to be careful of an argument from ignorance too.
Yeah.
That's what you got to
the logical error there is that a couple of them is a lack of counterexample in a statement that has not been proven true does not indicate truth or falsehood. Mm-hmm. Just like the lack of a proof does not indicate truth or falsehood. It just means we don't know.
Yeah, could you not make a probabilistic argument of some sorts though?
Well, again, that gets back to like we've been trying to find counterexamples, so we feel this conjecture.
So you can say something along as it is thought that it is this, but is no.
We are pretty sure that a counterexample is not going to come out. It doesn't. Just like in statistics, right? I can use statistical decision theory to say this. I'm going to reject my null hypothesis. This is most likely not due to chance. Does that mean that statistic that I observed is not due to chance? Not in the slightest. It means that it's highly improbable that it is, and therefore it is best for me to make the decision under the assumption that something besides chance governs it. That does not mean I have proven anything.
And
it
that's
does
the main
not
reason.
mean,
oh, good.
Yeah.
I'm sorry. Go ahead.
Those logical errors, right? The only thing that validates a statement is either I prove it or I find a counterexample that shows it false. That is it. Anything that isn't that, and you just don't know. Not for sure.
But that's the reason why in scientific papers they never say that they proved anything. That's why when you see some kind of headlines in pop science, they'll say, "Oh, scientists proved this," and as soon as I see that, I'm like, I don't know if I want to read it, right? Because no scientist has ever proven anything, unless they're doing something in math.
Yeah.
Math, you can prove
Yeah.
stuff, logic, you can prove stuff. But
'Cause-
they say in a paper, we believe it to be the case because they were able to reject the null hypothesis in their experiment.
Right. What they should say, and obviously forget the headlines, because I don't blame the authors of the original papers, because, you know, most of the time, if you talk to the authors of original papers like that, they'd be like, look, we didn't say prove. We said there is strong enough evidence to suggest a causal relationship, for example. Like, you know, most authors, like I said, leaving aside the social sciences, most authors in like a chemistry or a biology or an ecology or physics, they're very careful about what they say. We have evidence to suggest that. We have very strong evidence to suggest that. They won't say prove, and because they know not to.
Yeah, well, one of the things is, again, as we said, once something is proven, if it can't literally be disproven because it was never proven to begin with. So scientists, I think, would avoid using the word proof because science changes, and you have to be able to build upon that. And you could be wrong in science. I'm sorry. Science can be wrong. That's the greatest thing about science, is that science learns from mistake. And science, as it goes along, gets stronger and stronger because it's learned from past mistakes.
Right. So that's why you won't see good people in the physical and biological sciences or medical community say we have proven X, Y, or Z. They won't say that, and I appreciate that as a mathematician.
They use medical techniques that are 200 years out of date. Now, granted, I agree with, like you said, math doesn't really change. A theorem that holds true 1,000 years ago holds true today and will always hold true.
Right, if it's been proven true. If we've created a counterexample.
But theorems, by definition, are proven true. If it has a counterexample, it wasn't ever a theorem.
That's right.
So that's why
I agree with that. Yeah, so we don't reevaluate and evolve in mathematics the way that physics, chemistry, biology have evolved. We simply build on what we have.
Yeah. So should someone discover an odd perfect number and publish the proof that it's a perfect number, then the question will be settled. And you can't say, well, in my opinion, they shouldn't exist. I'm like, no.
We found one. There it is.
You know what? Why did you do that for a thing for your students? Because remember that time when somebody had put something on the board for their students to prove and know that it wasn't something that was proven before? They were just messing with their students.
That's not nice. My analysis professor did that to me as an undergrad on an exam, and it was horrible.
But can you imagine being that one student that says, "Yeah, I found a perfect."
Well, I mean, when Lamer was tutoring me, he would leave me with questions, and he'd say, "These questions are either trivial and expect you to come back the next time with the answer, or they're difficult and I expect you to show progress and tell me why the particular step you got stuck on was hard.
Yeah, I thought
or there have not been decided, and I expect you to come and tell me, they're unknown, and I expect you to tell me, at least make some progress or why the problem is difficult, right?" And he said, "I'm not going to tell you whether it's trivial or not, and you sometimes could not."
Trivial.
Trivial can be sometimes. The statement can be quite trivial.
Mm-hmm.
Yeah, I love that word trivial in mathematics because it doesn't mean what people think it means.
But he was pushing me and giving me, and so I had everything from unsolved problems to that, and on occasion, you can come in with insight that other people don't have. I mean, Erudish gave me 2 problems that were undecided, but I didn't know they were undecided. He just said, "Here's a couple of things you might want to try." And I didn't know they were hard, and I solved.
I love that. I didn't know they were impossible to do. I just did it.
But that was because I came in from a different approach, right? And they hadn't thought about it that way.
I've actually had that happen from engineers. If I've talked to an engineer and I've been into something too much, I've actually straight up, asked an engineer. They look at my board like, "So what is this thing?" And I've completely ignored it for 3 months, and I was like, oh my gosh.
But Rachel, I thought your trigger was the proof is left to the reader.
So to me, here's what a proof is. It's not just a statement that shows something is logically correct. I'm right, you're wrong, ha ha ha. The goal when I'm writing a proof is I'm studying a phenomenon, a thing, and my proof is supposed to help explain how it works. Not just
express that.
Yeah.
Right. So and this is where I algebraists and I kind of butt heads. There are some mathematicians that it's like a game, right? How few lines can I make for proof? Like, how few lines can I write code? I have respect for that. But sometimes, if even just starting the proof, like, why did you start there? Why? How'd you come up with that?
I understand the need to be compact, and I get that. But okay, so for example, when I write certain things, I don't really do proofs, although I've done some before. But I like to write blogs. I like to write different things, and I'll put something, but I'll actually show a little bit of detail why I got what I did or where I said what I did, more for the fact that, one, to show that I'm actually able to explain it, right? I'm not just pulling out my ass. And two, I want the reader to understand it. I want them to look at it and go, okay, I see how you. As a matter of fact, when on the Great Debate Community YouTube channel, I did a couple mathematical presentations. Like I explained how to use a Taylor series, right? But each step, I showed exactly what was going on, even though to the mathematician it would be considered to be, a given, right? But I wanted to show, and each time I did a mathematical thing, what was the steps being utilized, so people had a conceptual understanding of it, because most of them didn't have much math experience, right? And so I break it down that way. But I can understand the need to be compact.
Audience. So if I'm writing, and if I were going to, I'll write the proof to be complete, so that at any level, reasonably, you should be able to follow it. Now, when I go present that, no, you're not going to sit for 2 hours while I go through all the arithmetic. So I'll present, my paper is the complete, unabridged, but then, it's because part of, me getting you to use my stuff is me showing you how it works. The presentation that I would give at an engineering conference for some of my research would be very different than the one that I would go in and give Landon privately. It would be very different. Mm-hmm. So that's where there's proofs, that's the big, long, I've shown it's true. But then after that, that's where the communication part comes in, that it's up to me, not just that I've proven it true, but to show you what it is, how it works, that it's true at the appropriate level that you need to be able to use it. And that's where, you might, if I came on, say your channel, like I said, this isn't to condescend or insult any of your audience. I would probably give them more of a sketch of the proof. Now, if you want the proof, I can produce it, but I would give you a sketch of the proof to give you an idea of how it works, because your interest in it would likely be, how do I use this? Whereas if I went to, say, like the AMS national meeting, I would probably highlight particular portions of the proof that would be of structural interest to mathematicians looking to use that for other proofs of theirs. So it would just be I'm presenting the same information. I'm just selecting a different kind of lens on it, depending on the audience and what they might want with what I've done.
Because oftentimes the answer is not as interesting as the method. And so, it's been published, we'll accept the proof, but where in your steps of the proof are there, reasoning that I can grab a hold of and perhaps go in different directions?
Yeah, that's actually probably a good
topic. The result.
I think that'd be good for another topic about how somebody would utilize certain things in mathematics. What good does it do in their lives, or how, even if it's not specifically into their lives, how other people might use it? Because I think a lot of people, like you said, you took like the 4-color theorem, and you said, okay, this is how we'd act if it was proven true. This is actually we'd use it for optimization for shipping. Okay, well, you know what? We might have somebody that works in shipping. They might be able to utilize something like this. But I think that they like tangible explanations. It's something they can use in the real world. And I think that most of the audience I have on my channel, they think in terms of, how does this apply to me?
Well, that's okay. That's what I literally sell. I mean, I develop the math and I sell you the IP. I sell you the application. So if you and if an audience member who's, say, a shipping expert or a logistics expert, sits and talks to me about my research and said, actually, if you think of your shipping problem in this way, then we could develop a better algorithm to help you optimize your shipping of chemicals, for example. That's now IP, and that's what you're paying for if you hire me. That's what you're paying for.
So Amazon, if you're listening.
As I say, so we have five minutes left. Maybe Rachel, you can talk about it. If someone wanted to get a hold of you to have a mathematician system.
Sure. So themathcitadel.com is my company website. There are now, it's by no means an exhaustive list. We do have a page of projects that we're currently working on they're applications as opposed to, here's our research. So for instance, we are looking into application of our research to anomaly detection or air particle studies or, network engineering, a couple other things. So that's just, you can kind of browse and see if anything's interesting. It's fundable. You get patentable IP in exchange for funding. It's that simple. You can reach out to me on Twitter at Mathpocalypse, and there's also a contact form on my website for other inquiries. Most of the papers I've published are on that website as far as the theoretical papers. There are a few unpublished ones because I gotta eat. I can't publish until I can eat, kind of thing. But none of the things that are on the project page are by no means exhaustive as far as applications of what we're doing. So yeah, check out the website if you're interested. Read the articles we've got on all sorts of random mathy things like fun distributions and weird classes of distributions, some coding theory. My co-founder wrote some good stuff on topology and one on Russell's paradox, just other fun things like that. We do book reviews too. If you're looking for good math texts, we spend a lot of time reviewing math texts if you're looking for self-study of different topics. I only review books that either I've taught from or I've read cover to cover. So
and your link is in the video description as well, by the way.
Yeah. So you can find me there, or like I said, Twitter's kind of the only main social media I really use.
And for folks for me, www.isla.com is one of my websites. Twitter, Landon Noll, that's LANDONNOLL. And I'm around on the internet and such. I should also, by the way, plug this particular T-shirt I'm wearing is from the Milwaukee Atheists. It's one of the Behold things. They're a cool group. You should go and check them out as well.
Well, I live in Milwaukee now.
Well, there you go.
Oh, you've got it. Yeah, I've got to connect you up with them, definitely.
I was gonna say, yeah, I live in downtown Milwaukee now. Ooh. So
she's just docked herself. I live in the universe, so
you can. Yeah, well, I mean, it's a big city, like.
I'm sure she doesn't like.
It's a big.
Yeah, go try to find her. Good luck with that. But I do want to
don't encourage this.
Well, you know what? If you ever want to go find Landon, wait till it goes down to the South Pole again, because again, down there you have a small little community that's about, I don't know, yay big when you're down there. Yeah. So you can definitely.
Yeah, you'll probably find him there.
You'll probably find him there. So.
December 4th, 2021, total solar eclipse, Union Glacier, and we'll go to South Pole afterwards. I highly recommend getting on the list. So.
Well, I definitely want to thank both of you for coming on. Landon, like I said, on Sundays, he's free, so hopefully we're going to have like a co-host thing with me and Landon. We're going to be doing more of these things, and hopefully, Rachel will join us when she can. We'll have other guests as well. If you guys have suggestions about what you want to see on this particular show, put it in the video descriptions or just message me. But I mean the video comments. I like to read the comments, so let us know what you thought of this. Again, this is our first time doing something along these lines. We're open to suggestions, whatever direction this goes. Yeah.
Actually, I didn't know that people care. Like, I don't know, honestly, if anyone cares about my stuff unless you comment.
I got to tell you, somebody actually put in the live chat, these are two of my favorite guests Steve has had, and I'm glad to see them on again.
Oh, well, thank you. Thanks. And I apologize for the errors I've made. Point them out to me so I can make fewer of them next time. Or at least don't repeat the errors.
And with that, I'm going to thank you guys as well. Thank you from all my Patreons. I appreciate all the support that you give this channel, as well as the Non Sequitur Show. And we'll see you tomorrow, actually, on Monday, with the Non Sequitur Show. Good night.
Good night.